Similar figures, what made figures similar, and then we talked about how we could find like missing angles, missing sides, things like that. Okay, today we're going to continue on with it, but we're going to also add perimeter and area to the mix. And then we're going to look at two figures and we're going to try to determine if they are similar or not. And we're going to try to talk about how we can make that decision. So first thing up here is talking about the perimeter of two similar polygons. So in this case here, they are already telling me that these two figures are similar. So we don't have to make that determination. We already know that they're similar. Now we're going to talk about their perimeters. So kind of to review what we talked about on Friday, I'm just going to make up some numbers here. Let's say that this one has side lengths of 1, 2, 3, 4, just to try to keep it simple, okay? We've got 4 different side lengths. If PQRS is similar to the first figure, let's say that it is 2 times bigger. That means all of these sides are going to be 2 times bigger than the original side, okay? So all I do is take each one of these times 2, and so we're saying all of these sides are 2 times bigger. On Friday, we talked about the ratio being 2 to 1 or 1 to 2, depending on if we go from small to large or large to small, right? Either one of those would be acceptable. When we talk about the perimeter of these two figures, how do I find the perimeter of a figure? What do I have to do? Add up all the sides, okay? So if I did it for the first figure here, 1 plus 2 is 3, 3 plus 3 is 6, 6 plus 4 is 10. So the perimeter of the small figure is 10. Okay, the perimeter of the larger figure. Let's add it up. 2 plus 4 is 6, 6 plus 6 is 12, 12 plus 8 is 20. If I write my perimeter as a ratio, I could either say 10 to 20 or 20 to 10, depending on if I went big to small or small to big. If I reduce that, I get the same ratio as my sides. So the perimeter has the same ratio as my sides, okay? And that will always be the case. It doesn't matter what kind of figure it is. It doesn't matter anything about that. And we'll talk about why do we need that. Why is that helpful, okay? Well, it's helpful because what if I don't know all the sides of a figure, right? Maybe I only know one side. I know one side here and one side here. I can't just add up all the sides, right? But I can use this relationship to help us know that the perimeter and what the perimeter might be based on that, okay? So let's go down here. A town plans to build a new swimming pool. An Olympic-sized swimming pool is rectangular with a length of 50 meters with a width of 25. The new pool will be similar in shape, but will have a length of 40 meters, okay? So it will be 40 meters instead. If you wanted to, you could redraw like both of the pools. An Olympic-sized pool is 50 by 25. The new pool that they're going to build has a length of 40 meters. We don't know what the width is, okay? Now, we could find the width, okay? But all we're trying to find out is what is the perimeter of the Olympic-sized pool and the new pool, okay? So for this one, I could find the perimeter of the Olympic-sized pool. Because what do I know about the perimeter of a rectangle? Or what do I know about the sides of a rectangle? If I know this one has a length of 50, what's the other length got to be? It's got to be 50. If this one's 25, then these both have to be 25. So I already know all of my dimensions here. Okay. And the perimeter of this would be 50 plus 50 plus 25 plus 25, which would be 150. Okay. So the perimeter of the big pool, the Olympic-sized pool, is 150. If I were to do a size change here and compare the sides of this, you have to compare length to length or width to width. You can't compare like 50 to 25, right? That doesn't do any good because you're comparing two lengths on the same pool. So I have to compare this length to this length or this width to this width. Well, we don't know the width over here right now. So I don't have anything to compare 25 to. So what we're going to do is we're going to compare the two lengths. I'm going to compare 50 to 40, and then I can reduce that to be 5 to 4. This is what we call our scale factor. A lot of times we'll use the letter K for our scale factor. We don't have to find the width over here. We could find it if we wanted to, but we don't have to. Because what we can do now that we know our scale factor, we're going to use our K value, and we're going to now compare the perimeters, okay? We don't know the perimeter of the small one. That's what we're trying to find. But we do know the perimeter of the big one. So the perimeter of the big one is 150. So we got to make sure we put that on top because 5 is bigger than 4. So this is the bigger number, so the bigger perimeter goes up here. We want to find the perimeter of the smaller one. And then kind of like we talked about on Friday, once we have a proportion set up, there's going to be a lot of proportions in this chapter. Now it's simply just cross multiply to solve this. Okay, so we're going to cross multiply. The best way to do this, and you can write it all out if you want to, but you don't necessarily have to because we've done this before. 4 times 150, and then whatever that is divided by 5. So what I've done is I've found the perimeter of this rectangle without even knowing the width. Could I find the width? Maybe, right? And if I wanted to find the width, I probably could have done it that way. But in some of these cases, we're not going to really want to do that, okay? And I'll show you why, especially on this next one. Also, make sure that this number is smaller than this number, okay? These two should be in the same ratio to one another. And that's the way you can kind of check your answer. The reason we don't want to find all of the sides, on a rectangle it wouldn't have been too bad. All I had to do was really find the width. On this one here, this right here, we have 1, 2, 3, 4, 5 sides. So typically, if I was going to find the perimeter of this figure, this pentagon, I would have to add up all 5 sides. But we can find the perimeter of this guy without knowing the length of all 5 sides. I don't want to find the length of all 5 sides. That's a lot of work, right? That would be doing a proportion 5 times. I don't really want to do that. I want to do one proportion that gets me to where I need to be. Okay, but in order to do that, I have to know the perimeter of one of the two figures. Well, this one I can find the perimeter of, right? Because I know all 5 sides. So let's find the perimeter of gazebo B. Add up all the sides for gazebo B. What do we get? Okay, so we're saying the perimeter of this bigger figure, gazebo B is just a little bit bigger, and we know it's bigger because the two sides that we can compare are 10 to 15. We know this side's bigger than this side, okay? Obviously we can tell by looking, but that also verifies it. This also is the only two sides that I can compare, right? 10 to 15. You can leave 10 over 15 if you want to. I always like to do the reduced form just so my numbers are a little bit smaller. So I'm going to go ahead and take 5 out of each one of those, and that leaves me 2 over 3. So this is what we call our scale factor. Okay? On that scale factor, we're going to use that. And here's where you got to be careful. When I set up my proportion, I want to know what the perimeter of the small one's going to be. I don't need to find all 5 sides. That would be a heck of a lot of work. Okay? So what we're going to do is we're going to set it equal to the perimeter of each one. Okay? We do not know the perimeter of the small one, but we know the big one is 69. So this one's a little bit different than the last one because I went small to big. Okay? It really doesn't matter if you go 2 to 3 or 3 to 2, as long as you stay in the same order. As long as I go small to big, small to big. And now once I have this set up, now I can cross multiply and solve. 69 times 2 divided by 3. What's that give us? How much? 46. Okay. And then we probably should label these. I haven't been doing a good job labeling, but 46 meters. We're talking about meters here. Okay. So I didn't find all 5 sides of this, but I did find the perimeter based on that. If I would have found all 5 sides and added them up, I would have got 46. But it's kind of a shortcut. And that's how we can use the ratio to find our perimeter. Okay, area. Area is a little bit different. Okay, for perimeter, we add up all the sides. I'm going to show you an example that we're kind of I think we'll make this a little bit, make it a little bit more sense. Okay, if I tell you that this one is 3 and this one is 6, okay, and I tell you that this one is 2 times bigger, then this would be 6 and this would be 12. Okay, if I tell you that this is a rectangle, what would be, how do I find the area of this rectangle here? How do I find the area of a rectangle? The inside part of it. Not the distance around. Base times height, length times width, however you want to say it. So here, the area would be 6 times 3, which is 18. Okay, over here, it would be 6 times 12. Which is 72. Okay? And so the rectangle is 2 times bigger, but how much bigger is 72 than 18? What's 72 divided by 18? 4. Okay? So the similarity ratio, or our K value, is 2 to 1. Okay, our area ratio is 4 times bigger, 4 to 1. Okay, and so we got to talk about where does this number come from? Why is it 4 times bigger? Because the rectangle is only 2 times bigger. Why is the area 4 times bigger? And that's because whenever we label area, whenever we talk about area, we're always talking about units squared. So we're going to square whatever that number is. So if I were to take this number right here and square the top and the bottom, what's 2 squared going to make? 4. And 1 squared would be 1. So that would make my new area ratio. Okay, and I'll show you why we can use that or where we can use that. Now I tried to give you an easy example of something that was easy to find. If I had something like this, I don't have a formula to find the area of these figures. It's kind of a weird looking figure. We don't have a formula to find the area of it. Okay, and so now we can find the area of any type of figure as long as it has a similarity ratio from one to the next. Okay, so on this first one, and once again, don't necessarily pay attention to what type of figure we have. Okay? And in the past, like if I was going to find the area of a triangle, I'd have to know the formula for the area of a triangle. We're not worried about the formula of these figures today. We're not going to find the area that way. We're finding it using the ratio of these. Okay? So first up, our K value. Well, we're going to compare the two sides that we know, 10 to 5. So our K value here is 10 over 5, which is 2 over 1. That's what we call our scale factor. So once again, not always like this, but this triangle is 2 times bigger than this triangle, is what this is essentially saying, right? If I wanted to find the area, I'm going to write a proportion. I'm going to use this, okay? But my area ratio is going to now be 4 to 1. So if I want to find area, I'm not going to use 2 over 1. I'm going to use 4 over 1. You got to take these numbers and square it. So now if I want to find the area, I got to use my area ratio. I'm not going to use 2 over 1. I'm going to use 4 over 1 because we're finding area. So in order to find area, we've got to use the area ratio. And what we know is that the big one has an area of 36. We're trying to find the area of the small one. Okay? So 36 is the bigger one. The smaller one, we don't know. That's what we're trying to find. So they're going to give us 1, and we're going to use it to find the other one. Okay? I'm not finding the other sides of the triangle or whatever figure we have. I'm just using those to find what we've got. So 36 times 1 divided by 4. Okay, when we label this one today, we're talking about the area of the smaller triangle. So when we label it, it's always going to be centimeters squared. So it's going to be 9 centimeters squared. The area here is 4 times bigger than the area here, is what we're really saying. Okay, so there's other ways you could have gotten there, but it's not always going to be nice whole numbers like that. Okay, so on this one here, the two sides that we're comparing are 7 to 21. Those are the only sides that we know. I can't choose any other sides because we don't know any lengths to any other sides. So 7 over 21 is what we're going to use. I'm going to reduce that. So what we're really saying is that the big is really 3 times larger than the smaller one. Okay, 1 to 3 ratio. To find the area ratio, we're going to square both of these numbers. 1 squared is still 1. 3 squared is 9. So 1 over 9 is the ratio that I want to use when I'm finding the area. If I'm finding area, I have to use the area ratio. So we're going to go 1 over 9 because we're finding area. It tells me the area of GHJK is 84. Okay, so where is 84 going to go? Is it going to go on top or is it going to go on bottom? Okay, how come, Leah? It's the smaller one, right? They tell me GHJK. GHJK is the smaller figure, right? 84 goes with the smaller one. So 84 has got to go on top because 1 is smaller than 9. If they would have given me the big one, then I would put it on bottom. We're trying to find the area of the big guy. So that's X. Okay, you're always going to have an unknown here. You also got to make sure you use the right ratio. Those are the 2 things you got to be really, really careful of today. Now as we cross multiply here, 84 times 9 divided by 1, really just have to take 84 times 9. What's that give us? Okay, 756. And our label here is just a little bit different. We're using meters here. So this would be meters squared, just like the other one. Okay, it's 9 times bigger is what we're saying here. Okay, questions on any of that so far? All right, let's look at this one down here real quick. What is the scale factor? Okay, which one of these three sides do we use? Okay, and this one's a little bit different, right? Because I know all three sides of all three triangles, right? On the one we did just a second ago, I only knew one sides that match up. So we only had one option. Here, I could go 12 to 3, 20 to 5, or 16 to 4. Does it really matter which one I do? No, because let's say we did 20 over 5. That would be 4 to 1. What if I wrote it 1 to 4? Is that okay? Yeah, it's the same thing, okay? What you got to be careful of on especially big ideas is it may ask you to say big to small or small to big, okay? And so it may ask for a specific scale factor. If not, it should accept either one. But if you try 4 to 1 and it doesn't take that, try 1 to 4, okay? So try either ratio if it doesn't specifically say what order you're going in. If I wanted to find the ratio of the areas, what do I have to do to the K value to get my area ratio? You got to square it. Good. So we're going to square both numbers. I'm just going to go 16 over 1. 4 squared and 1 squared. Okay? I'm not going to do both, but you could do 1 over 16 if you wanted to. The ratio of the perimeters. Okay? We're not asking to find the perimeter. We're asking to find the ratio of the perimeters. The ratio of the perimeters is the same as the ratio of the sides. So it's also going to be 4 to 1. The perimeters are going to be 4 times bigger. The ratio of the corresponding side lengths. So as I compare side to side in any combination, they're all going to be 4 to 1. So when I talk about sides, scale factor, perimeter, they're all the same. When I talk about area, area is the one that's different. Area has to be squared. Area is the one that stands out. Okay, last page. This one, what we're trying to determine is, are these figures similar? Okay. This kind of goes back to what we talked about on Friday a little bit. And I know it's been a little while, but this is a good review of what we talked about on Friday. You're going to have some problems today. They're going to ask you, are these two figures similar? Well, there's two things that must be true. In order for two figures to be similar, what's one of the two things that has to be true? Let's start with angles. What would be true about angles? Angles must be congruent. Okay. Okay, sides do not have to be congruent, but the word we use here, all sides must be proportional, which means they all make the same ratio, the same scale factor. Okay? If one of them is different than the rest, then we would say, no, it's not going to work. Now, I don't love this problem because there's one thing that kind of sticks out about this problem that I always tell you don't go off of looks, and this one goes off of looks. But the first thing I'm going to do here is I'm going to show you the side lengths. So 12 would match up with which side on the red figure? Yeah, 8, right? Now, sometimes we can look at it. This one's been flip-flopped, but remember to pay attention to the letters. So like AB is going to match up with KL, okay? So AB goes to KL, so 12 over 8. Okay, and then BC is 9. 9 is going to match up with QL. And notice what I'm doing here. I'm looking at BC and QL. The next two letters are CD. CD is 6. And RQ is 4. Okay, and then we would do DE, which is 9. It's going to match up with RP. And we got 5 sides here, so the last one would be AE, which is 12, and it's going to match up with KP, which is 8. Okay, now here's what we want to do. We want to see if all of these reduce to be the same thing. Notice that some of them are the same, right? So we don't have to reduce it twice. If I reduce 12 over 8, what's something that goes into both 12 and 8? 4, okay? Make sure it's the biggest number. We might look at it and say 2 goes out of that, right? But we want the biggest number we can take out, which would be 4. 4 goes into 12 3 times. 4 goes into 8 twice. Okay, 9 over 6. 3 goes into both. 6 over 4. 2 goes into both. 9 over 6, we already reduced it. 12 over 8, we already reduced it. Okay, all of those are the same ratio, which they have to be. Okay, so are all the sides proportional? Yes. Okay, now here's the part that I hate. I don't really love this about this problem. Okay, all we have is one angle that's marked. Okay, but as I look at this picture, okay, what angle does R match up with on the other picture? R would match with D, right? And we could even go D to R. As you look at D and R, what do you notice? Do they look to be the same? Not really, right? You see how R looks like it's a little bit more flat than D? Looks like it makes a little bit different angle, okay? I have always told you don't go off of looks, and so this is one that, like, I wouldn't give you a problem like this on a quiz or a test, right? But this is one that we kind of picked out. And so if I looked at these two, because R looks a little bit different than D, then we would probably say that these two are not similar, because angle R is not equal to angle D. And I'm just going to write here that it doesn't look like it. We can't really prove it. We don't really know. And that's what I hate about this problem is I don't like to say, it doesn't look like it, okay? They don't look the same, but we really don't know a way to prove it, okay? So probably what I would do on a problem like that is I would say prove that all of the sides are proportional. If the angles, if we don't have any way of proving the angles, I would say don't pay attention to the angles themselves. But that's what I don't like about that picture. Okay, on this one here, these are 2 different problems. So let's start with this one here, okay? The red is a regular hexagon. Decide whether the hexagons are similar, okay? So what does it mean when it says regular? Right, okay? So we know the red one, all the sides are congruent, okay? We don't know that about the blue one, but as I look at the markings on the blue one, what do we know? They have different side lengths, right? Like this one, they're all the same. This one, they're not the same, okay? So can I compare the red one to the blue one? No, like here would be the best example. Let's say that this is 8. Well, it's 8 all the way around, right? All the sides of it are 8. Well, in here, maybe this one is 6 and this one is 5. If all of these were 6, then they would all be in the same ratio, right? But because one is 6 and one is 5, then they can't all be in the same ratio because all the sides on the outside are the same. Okay, so we would say these two are not similar, and we would say because the sides are not proportional. Once again, that's a big word for today that we got to pay attention to. Now, if I look at the second one, we don't have the sides on the red one marked, but it tells me right here the red outer shape is a regular hexagon. So what's that tell me about all the sides on the red figure again? They're all the same, okay? And so once again, if I gave you an example, like if I told you this was 8 and this was 6, then all of the sides would be 8 to 6, all the way around. I'm not going to write it 6 times. They would all be 8 to 6, right? So they would all reduce to be the same thing. They would all reduce to be 4 over 3. So here we would say, yes, it is similar. And we would just say something about all sides proportional. And you could say the same thing about angles in this one as well. All angles are congruent, because if both figures are a hexagon, that means all the angles are the same, because it's a regular hexagon. Okay, these last two asks us the question, are they similar? Okay, and kind of like I was saying up above, because we don't know any angles here, we're only going to base it off of the sides. So as we look at this, we got to decide which ones go with which, right? So let's start with the biggest one over here, 20. What side will 20 match up with on the other figure to the right? Okay, how come? Yeah, because over here, 20 is the longest side, right? So over here, we got to match it with the longest side over here. Biggest has to go with the biggest. So 20 has to go with 10. Don't pay attention. Oh, this one's on the left and this one's on the left, so those two are the ones that match up. Not necessarily the case, okay? Biggest goes to biggest. And then I just kind of like to work my way around. 18 would be the next biggest. So it's going to have to match with 9. And then 16 matches with 8. And finally 10 matches with 5. If I reduce all of those, what do they all reduce to be? 2 over 1. So we would say, yes, these are similar. As long as all angles are congruent. If I did the same thing on the next two, and I went big to small, 14 is the biggest one here. 8 is the biggest one on the other one. 9 goes to 6. 6 goes to 4. 3 goes to 2. Do all 4 of these reduce to be the same thing? These 3 all reduce to be 3 over 2. But if I reduce 14 over 8, I would take 2 out of each one of those, and that reduces to be 7 over 4. Or 7 over 4 and 3 over 2, the same ratio. Okay, so because these two are not equal, then we would say these two are not similar. All 4 lengths must be in the same ratio in order to be similar. Okay, if 3 out of the 4 are, that's great, but it's got to be all 4. Okay, so those are the things you got to really, really pay attention to as you